I'm recording now, no worry. Okay, yeah. So, yeah, I think you are busy with the assignment right now, right? But anyway, yeah, we start with the new topic. So this one this week last 2 weeks we learned about the hash table and the graph, and then breakfast search, breakfast search. Then now we going to another very important algorithm, so called the backtracking algorithm. Okay. So I think okay. So what is the backtracking mean? Okay. So suppose that you make a series of decisions, and for each decision, right, you have various choices. Okay. But at one time, right, you don't have enough information to know what to choose every step. It means that like you are going to one stage and there are many choices, but you don't have enough information to know which direction you will choose to go. Okay, and each decision will lead to the new set of the choices. It means that when you choose to go one path, right, then you go to another choices, new set of the choices, and then in the subsequences of the choice, maybe more than one, right, it will be the solution of your problem. Okay, so to make it clearer, so the backtracking is a methodology to try out various sequence of the decision until you find the one that work. Okay, to make it clear, right, I give you one illustration. Okay, for example, you have the starting point. Okay, at first you have no clue about next. I mean, you just know that okay, you have a few choices. Then you choose one choice. Okay, and that's you go right. Then you have a few choices, but you don't have the enough information to see which choice you will go to get the goal. For example, you have the goal at the end. Okay, then you choose one path to go. You have many choices, so you choose one choice to go. Then you go, you face another choice. And again, you don't have any information about which choice you will choose next. Okay. Then you just pick one choice to go. Then at that choice, you face with the dead end. It means that you cannot go to the like desired goal, right? So you cannot go anymore. So they're gonna dead end. Then what you do next? You back to the previous choice. Okay. Then now, because previously you choose one choice, you go to the dead end. So you make another choice. Okay. From the previous stage. And for example, it also the end. Then you go back to this stage. And suppose that at this stage, you have no more choice to go. So what you do? You backtrack the previous state of this stage. Because now you at the current stage, right? Suppose there are only two choices, but you already tried two choices and no choice work. So you will backtrack to the previous one. Okay, backtrack to the previous one. And suppose the previous one have another choice to choose. For example, this one. Okay, so you go this one. Then again, this one have a few choices. Then you just pick up one to go. For example, they lead to another choice. Then it dead end. Then you need to go back. They call it backtracking, right? Whenever you choose one path to go, if they're dead end, then you go back. Because it haven't come to the solution yet, you go back. You go to another choice. Yeah. And until you cannot go anywhere, you back to the previous stage. Okay. And then you go this way. For example, you get this way and another choice. And you face another choices. Yeah, the next choices. Then you go. The end, you choose another one. Success. Then you stop. Okay. So it means that's the idea of the backtracking. Backtracking can be called like go. I mean, just try and go back. It means try, cannot success, go back. That's it. So whenever you have the choice, you just pick up one choice to go. If you cannot go anymore, you go back. You choose another choice. Yeah, that's the idea of the backtracking. Okay, understand? So very simple, right? The idea very simple. You face so at one stage you have a few choices. You don't know what to do, right? You just pick one choice to go. If this choice cannot work, you backtrack to the previous stage. You choose another choice. That's it. Very simple one. Okay. So for the backtracking, right, there are many problems that you can use the backtracking algorithm to solve. For example, solving a maze. Okay. For example, you have the starting point here, and you need to find a path that you can go out here. Okay. So this is the goal, right? We need to go out here. Okay. So for every step, right, you can see that either you can go straight, or you turn left or turn right, right? Every stage, yeah, you have a few choices. Go straight, turn left, or turn right. Then you need to find a path that you can go out. Okay. So of course, for example, when you start here, right, you don't have information about the choice, right? For example, from here, you can have two way, right? Either you go straight, or either you turn, this one called turn left, right? Okay, yeah. Either you go straight or turn left. But which one you choose, you have no idea, right? So you just choose one. For example, you go choose this way, okay? Go this way, you face the dead end. Then for the backtracking, right, you just go back and you pick up another way. So you go this way. Similarly, yeah, right, you go to this stage. For example, go to this stage, right? Then you have a few choices, right? Turn left or turn right, right? Then you just pick up one to go. If not successful, then you go back to choose another path. Yeah, that's it. Okay, so this is exactly the backtracking algorithm. Okay, so that's it. One choice, right? At every stage, you choose one choice, you lead to another choices. Yeah, and one more sequence may not lead to the solution. For example, you go this way, you face the dead end, right? So you just go back. Yeah. So many types of the maze problems can be solved using the backtracking. Okay, so there are one problem that you can use a backtracking to solve. Another problem, very famous problem, they call the coloring a map. So the problem very simple. You are given a map, okay, with many regions. Okay, so like different stage. Like this is the map of the US, right? Then you have the 54 stage, and you want to wish to color a map such that the adjacent region doesn't have the same color. It must be mean that the adjacent region must be in the different color. Okay. So they are map. So you are you want to find whether, for example, given you like 3 colors, 4 colors, or 5 colors, whether you can you can draw the map with this color so that the adjacent regions must be in a different color. That's very simple. So actually, this one is a very famous mathematical problem. Frankly speaking, yeah, this is a very famous one, and this is still the unsolvable mathematical problem. The problem, the mathematical problem here is given any map, right? Given any map, actually, you can use 4 colors, okay, to color the map so that the adjacent region will be have the different color. There's a way to color any map with only 4 colors to satisfy the condition that adjacent region must be different color. So that's the unsolvable mathematical problem right now. Yeah, even though like the problem stage for a few hundred years right now, but the current mathematician still cannot solve it. I mean, if you have any solution for this one, you can get a $1 million prize, $1 million prize. They are given $1 million prize for anyone can prove that problem. Okay. Yeah, the rough coloring. Yeah, any problem that use backtracking can be used in the. This one can be used to scheduling the exam for the student. Yeah, the same things, right? Monte Carlo used in this problem. Yeah, you can use also. But this one is for the the computer, right? But the general problem is given any map, any type of map, whether you can prove that any map you can use a four color to color this. This is the open mathematical problem. But anyway, we are in computer science, right? We just solve it using the the computer ways. It means that we are given the input, right? We need to bring down the solution to draw this map. Okay. So for our the computer science, the coloring map can be solved using the backtracking algorithms. Okay. Later, I will tell you how to do that. Okay. So again, right? For example, at the beginning, right? Every stage here is empty color, right? Then when you face with one stage, right? You don't know which colors you need to choose. Okay. So you just choose one color and you color another one. Okay. The adjacent one. Okay. Then again, you also have a few choice. You don't know, so you just choose and try. If not successful, you go back to choose to color it with a different color. Okay. So yeah, also a backtracking algorithm. Okay. Yeah. So this one can be solved using the backtracking algorithms. So many other, of course, there are many other problems that can be solved using the backtracking. Okay. The scheduling exams for the student, you can also solve using the backtracking. There are a way to solve this problem also. Okay. But anyway, back to our methods. So we know about a few problems that can be solved using a backtracking and what is the backtracking problem, right? But how we can program the backtracking in the computer, okay? So how we can implement this algorithm, okay? So that's a few terminology for you. So you see, right? The backtracking algorithm you can consider like a tree of the decisions, and some decision may face with the dead end. It means that you cannot go anymore, so you need to stop. Okay. Then maybe they want, like for example, one successful, maybe they are successful, maybe. Yeah. This is on the dead end. Yeah, on the dead end stage. Okay. So you can consider the backtracking is searching a tree so that you can search for the goal leaf node. So for example, this one. Okay. And every stage you have a few decisions. Okay, a few way to go. Okay. Then normally you have the root node, right? The starting point. They call it root node. And the internal node. It means that at every internal node you have some choice to go. And the leaf node means that at that one you cannot go anywhere. So this one either the dead end node or the successful node. Okay. And the backtracking is the way that whether you can find one successful or the goal leaf node or not. Okay. So how the backtracking algorithm we can implement? Okay. So actually the backtracking you can see very simple, right? For every node, for each node, right? You just explore all the possible solution at each node. So for example, you are facing with one not end. You are now at the not end, right? And there you have a few choices. Then how you do? So if n is the goal not, it means that the solution, right? Then we just return success, right? We don't need to go anymore, correct? Because it already, okay, this is already success. But if n is the leaf not, so now we are facing the end, right? So if n is the goal, then you stop, of course you stop, you return success. If n is the leaf not, but it's not the goal, the goal not, it means that it's a dead end not, right? Then you just return failure, right? Because you cannot go anywhere, right? So for one not, so when you go here, if they are dead end not, then you just return failure. If they are goal not, then you just return success. If there are a few choice, then what you do? Then for each child, right? You have a few child. See here, see here, see here, right? So for each child, you just explore this child. Okay. Okay. For example, you go this way, you explore this one, and you just continue blah 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 something. But we don't care. We just say that okay, we explore this one. If this one later return success, okay, return this one is the correct path, then you return n is success, right? Otherwise, if on the path return no, okay, so on the return no, cannot go this way, cannot go this way, cannot go this way, then of course we return the result for not, this not also no, right? Cannot go, right? So very simple, right? So when we face with one not, we check, okay, whether this is a goal or not. If a goal, we return success. If they are dead end not, yeah, no, cannot go anymore, then we just return failure, okay? And if they have a few choice, you just try on the choice. If on the choice, if any of the choice return success, then you just return success, right? Because for example, this choice return, oh yes, then you just return this one, oh yes. Let's say go this way, we can find the solution, okay? So you just return this way, yes, okay? Otherwise, if on the path is no, this means that cannot find a solution for on the path, then you just return the not for any no, yeah, the failure, okay? So it's quite simple one. How to know it's success? It depends on your problem, right? For example, in the coloring problem, success means that you go to the last region and you can color the last region, and that is success, right? Because you color the last region and it doesn't violate the condition that on the adjacent region will have a different color, then you can say that it's a success. Or for the finding the maze, right? Success means that you can go to the gate, right? That is success, right? So it depends on your problem. Yeah, you can define what is the success, what is the unsuccessful. Okay. For example, for a maze, if you can go to the gate, then it is success. Yeah, this is a good question. So how we can implement it? Whether we can the depth search. Actually, the depth search, you remember depth search, right? Depth search is one special type of the backtracking. Okay. But how we can remember the state to go back, apply something, right? There are many ways to do that. Okay. There are many ways to do that. So one way is we use the recursive function. Okay. So this is the most common way to use for the backtracking algorithms. Okay. So the student mentioned in the context of tree, we had a special called the dead end. Yeah, the dead end means that we cannot go anywhere. So it's just a one condition, right? You go to this stage, then you cannot go anywhere. And this stage is not also the goal of our methods. They is dead end. Yeah, definition. Yeah, when we design the algorithm. So later I will show you one example how you design the algorithm to show, okay, this is the dead end or this is successful or something. Okay. So back to these algorithms, because every time, right, we need to remember the stage. Remember, so that we can backtracking, right? Because maybe we can go a few ways, then we need to backtracking a few steps, right? So how to do that? So the common ways is use the recursive function. So why the recursive function? How we can implement this using the recursive function? So that's it. So you remember for the not, right? So the recursive function also work very similar. So when you go to the one not, right? So you call it a backtracking n. Okay, one not n, right? So if n is a goal, so return success, then we just mentioned, right? If n is a leaf not or the dead end, right? It's not the goal, and it a leaf, it means that it's the dead end, right? Then we return value like the previous one, right? Then for every child, we just call the backtracking for each child. Okay, so we're backtracking for this one. For example, if we number is this one, for example, n, right? This one we call the n plus 1, right? So we just call the index n plus 1. Okay, backtracking. Then remember, right? We just call the backtracking for this node. And maybe this node, after you call the backtracking, right? For n plus 1, right? Or backtracking, okay, maybe n plus 1 is maybe difficult for you to understand. I just use a C like in this one. Okay, they have the child, right? Call the C, right? So you call the backtracking n here. Okay. Then the backtracking n will call the backtracking C. Okay. You see? The n will call backtracking C. They are recursive function, right? And later the backtracking C will check on the child, right? Then maybe they go to they call it backtracking maybe like D or something, D a child C, right? So it just continue, right? And if, for example, backtracking C, right? Because you can go and way down further, right? Then if backtracking C, whatever you do, right, for the recursive function, if return true, then you will return this one true. Okay. But if on the child, so it means that you go this way, you return no. This way can be how many ways to go, right? But you assume that you got the result no here. Then you just return no here. Okay. Then no here, you will return, yeah, to the backtracking end. No. Okay. So that's the way for the recursive function work. Okay. Understand why the backtracking work, right? You have one node n, right? And you have a few child. So you just call the function, okay? For example, backtracking one child C. For example, you have a few child C1, C2, C3, right? Then we just call the backtracking BC1. Then BC1 will continue go, right? Blah, blah, blah. We don't know. But it will return one result, yes or no. This means that the path here, right? Yes or no, okay? Yes or no, okay? Or success or failure, okay? If C1 return success, then it means that there's the one way to go. Then you just return n success, okay? Yeah. Sorry, n success means that yes. Yes, okay, right? But if on the path, because you call the recursive function, you don't care because later it call recursive again, right? In the later path. But for example, don't care later because it's just a recursive function. So, but it's on return no, then of course it will return no. So that's why is the way we can do the backtracking. Okay. So if, for example, you can't from n, right? You can't see one, right? Then how you can know that, okay, if C1 cannot go, how you can choose another pack of choice? You just return C1. C1 no, or return no, right? Then you just return n. You choose another one. Yeah, you can do kind of form for all the childs. You choose a C2. Okay. If C2 also return no, right? Then you choose another child until one child return yes, then you return success. Okay. Yeah. If any one child return yes, you return success. If the child still return no, then you just choose another child to go. Okay. Until all the child return no, then you return back no to the parent node of the n. For example, reverse node of the n, the starting point, right? Starting point go to n. So if on the child of the n return no, then you just return no to the starting point, for example. Okay. Then this one is just about return yes or no. Then you can ask whether we can count how many successful, right? So it means that you just modify this algorithm a bit. So this one is one success, right? Then instead of returning, right, you can count, right? Instead of returning, it means that you found one child is success, then you stop the end, right? You stop the for loop, right? You can continue. So it means that instead of return success, then you make a count. How many success? Count equal count plus one here, right? Right. Then you continue to check on the child. Okay. So this is the way that, okay, for many problems that you want to count how many successful stage. That instead of, okay, there one successful, you stop, you can just count how many successful here. Make a count equal count plus one. Right? Then you continue another child. Yeah. Okay. So that's the idea for the backtracking. So many of you maybe imagine how we check whether success or failure or how the real implementation. Okay. So this is we back to the coloring problem. Okay. So given you a map, okay, like this, then you want given you a few color, for example, okay, if our input is a graph, like we mentioned, right? V times V is just like the matrix representation, right? So it's if they're adjacent, then you put one. If not adjacent, you put zero. For example, this one is one. The state we just number is the stage. For example, this one is 3, this one is 4, this one is 5, right? For example, like this. Then you just start the adjacent matrix, correct? 1, 2, 3. For example, we have the like V, right? V stage, okay, or V region, 3, and V. Then, for example, 1 is adjacent region of 2 and 3, right? So 1, 2, and 3, you just put 1, okay? The rest you just put 0, for example, okay? Because 1 only connect to 2 and 3, for example, okay? Or 3 or 4, right? For example, 4 connect to what? 4 connect to 3, 5, 6, 7, right? For example, the red color, this one is 7, sorry, because they are red color, so I cannot draw. So for example, this one is 7, okay? So the red color here below the 6 is 7, for example. Okay, for example, this one is 7, I cannot draw, okay? So it means that 4 will adjacent to 3, 5, 6, 7, then 4 to 3, you just put 1, 3 to 4, you put 1, something like that. 4 connect to 5, I mean the adjacent to 5, so 4 to 5, 5 to 4, for example. Yeah, it means that they are adjacent, so you just put 1. The rest you just put 0. Okay, so you can store it as a graph, right? It's just like the adjacent when you represent the graph. You remember, right? Last time in the node, right? So we just also put like that. So if they're adjacent, you put 1. If not, then you put 0. Okay, so there are ways that we can represent the adjacent matrix, right? Okay. Then the input is just a number of the color. For example, they are given you 4 color. Okay. Then the number of color n. Okay. So what you output array of the color. Okay. So for example, you have the V region, right? So this would be the V. Okay, the length of V. Okay. Sorry. Then for each number, you just put the number from 1 to m corresponding to n color. For example, the first, you mean that the red. I mean the number 1 mean that red. Second mean that the blue. 3 mean that the yellow. 4 mean that the green, for example. Okay. So for example, 1, right? You can, I mean, for the you can find one. You can find one solution, right? For example, this is one solution. For example, this is the output. Then what the output actually you present? 1 is green, right? Green. So this is the stage, right? The index is the index number of the stage, and because the first one is green is 4, so the first one is 4. Okay. The second one is yellow. Yellow is number 3, right? Yellow number 3, so the second one is number 3. So the index here 1, 2, up to V, right? So it's just the index of the region, and the number is the color number. Okay, because you have m color, so the color number. So for example, you encode is like the number from 1 to m. Okay, for example, number 3 is red, right? So number 3, so it means that the stage 3 you put number 1, right? Because the red is number 1, right? Okay, so understand. So that's the way we encode the input and output. Okay. Then at the end you should return this one. Okay. How we build the input adjacency matrix? This is the input they give you. They give you. It's just a one way, right? One way to represent the adjacency. It's just like the 2D array, right? Or 2D, they call it 2D array or 2D adjacency matrix. Okay. It's just like you remember we represent the graph. Okay. And the matrix is just represent the adjacent stage. If they are adjacent, then you input 1. If not adjacent, you input 0. Okay. And the index is just the index. For example, 1 to 4, right? 0 means that 1 and 4 are not adjacent. And you mentioned how can we build the adjacent matrix? They will give you the input. Okay. For example, they give you, okay, this is on the adjacent list. For example, 1, 2 is adjacent, 1, 3, 2, 3. Then you just build the adjacent list, adjacent matrix, right? To just represent it. It's just like exactly like you do the adjacency matrix for the graph representation, right? You don't know which color will color V. Okay, so I mean the output. I mean you need to output, right? I mean the matrix is just the one type we store the information. Okay, you can use any way adjacent list or whatever. Okay, so matrix is just one way to store the information of the adjacent C. Okay, you can use whatever you like. For example, you can use the adjacency list, right? For example, one is adjacency with 2 and 3, then you can create a linked list or whatever, like adjacency list or adjacency matrix, right? So for example, in this one, we use adjacency matrix, okay? But you can free to choose as long as later you know which one is the neighbor with the orders, so that you know, okay? So when the people give you the input, they just, okay, this is on the neighbor, okay? Then you need to store somehow, okay? So, okay, that's the, okay. Then the output, you understand how we output, right? Because we need to color on the stage with particular colors, right? So we just use the array with on the stage, okay? The index of the stage will be the index of the region. For example, V, right? This is the V, okay? V, okay? It's just array of V, okay? So the index 1 means that the region 1. Index 2 means that the region 2. That's it, okay? Then for each region, we need to color. So we just assume that, okay, the first, the number 1 is represent the red, number 2 represent the blue, number 3 represent the yellow, number 4 represent the green. It's just, your definition, right? Okay. We just assume that, okay, 1 is red, 2 is blue, 3 is yellow, 4 is green, okay? Then, for example, in this is one output, right? So you need to bring down this output, right? So for example, you know that, okay, the state 1 is the green, why? Green, then you just look at, okay, state 1 is green, green is number 4. So you put number 4 here. Okay. The state 2 is yellow, right? State 2 is yellow, yellow is number 3. So it's just number 3 here. Right? So that's it, the way, later when you output this array, okay, then you can understand how we color, right? Okay, we know that, okay, the first one we color with number 4, it means green. The second one we color with number 3, it's yellow, okay? Yeah, we choose, your definition you can define, right? Because or you can just, okay, you don't need to put a number, you can put, okay, or you directly the array of the string also, you can directly, okay, the array of string, so directly use the number. You can use yellow here, you can use number 2 is oh sorry, you can put like array, right? The first one you can put what one is green, green, yeah. This is the yellow, this is the red, yeah, whatever you want, okay? You can array up the number or array up the character or whatever, okay? Okay, so just the output, you can encode it 1, 2, 3, 4, you can encode it like red, green, blue, yellow, green, whatever, okay? Just use the 1D array. Okay, understand here, right? You understand the input and output, right? Input is just a way to index, so that you later you know which one is the neighbor of the orders. Okay, and output is just a way that we can output. Okay, we need V stage, so we need array of V. Then every value will be the corresponding to the color. Okay, so understand here. So simple, right? Okay, now how to solve this problem? So very nice way is you check all the possible combination. For example, you have the M color, you have the V, V stage, right? Or V regions, right? Then for each region, you have the M color, right? Then you check you check all the combination of the V. Okay. For example, you check, okay, all the combination on red, then red, green, yellow, red, green, blue, blah, 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 yeah, all the combination. So the number of the combination will be, because every stage, every region, you have M choice, right? You have M color, and you have the V region, right? Okay. So it means that the number of the different combination will be m power v, correct? If you just do the brute force search, check on the combination, see which one is corresponding, which one satisfy the condition that the adjacent region must be in the different color. So you check on the combination, and every combination you check whether it satisfies condition or not. Okay, this means that you need to check m power v combination, right? Because each region have m choice, and you have the v region, so the m power v. But imagine, right? If you have four color and you have 64 regions, then you need like 4 power 64 combination, right? To check, correct? Then with the current super power machine, right? You need billion years to check on these combinations. 6 power 64 to check on these combinations. So of course, this is a very nice solution, right? Okay, so we need a better way. So the better way we use is using the backtracking algorithm. Okay, so how to use a backtracking algorithm to solve the problem? Like, for example, we have the 4 stage, for example, and okay, we back to the graph. It means that if they the path, it means that they are adjacent. Okay, for you to easy to observe, right? Oh, sorry. This one I just updated. Maybe later I will update the slide in the ATU Learn. Okay. This is I just update so that you can easy to observe. Okay. After this lecture, I will update the new slide into ATU Learn. Okay. So A have the connection to B and D, mean that A is adjacent to B and D. So A must have the different color with B and D. But similarly, B have the different color with A and C. And if you have the four region like that, so actually you can use only 2 colors, right? 2 color. Okay, you color just A and C is the green, B and D is the blue. Then you satisfy the condition, right? Any adjacent region will have a different color, right? For example, A and B is the neighbor, so they have a different color. B and C neighbor, they have a different color. Okay. So how the backtracking will do? So at first we want to color A, right? We start with, for example, A, right? We want to color A, but at this point we don't have any information. So we just, for example, we color A in the green. We follow this path. Okay. Then you color the next one. You color the B, right? Then you color B. You also have 2 choices, right? At this stage you have 2 choices to color B, right? Green and blue. For example, you color B is the green, but B green, A green is not satisfy the condition, right? Because AB is a neighbor, right? So you can stop here. Okay, then you backtrack. Okay, so you said okay, B green is not the B green is the dead knot. Then you choose another choice of B, like blue. Okay. Blue satisfy, right? Satisfy condition. You can satisfy condition. Now you color A and B. Then what next? You just color C, right? C again. You have 2 choices. For example, you have this choice, blue, C blue, but C blue is not satisfy condition because B and C are adjacent. Okay, so you stop here. Then you back to the C green. Okay, C green. Then you have 2 choices for D, right? So if you color D green, it's not satisfied, so it dead end. Then you color D is the blue. Now you find the solution, right? Sorry, what's wrong? Okay, now you find the solution, right? This is the goal, right? Because you already color four regions, and this satisfy the condition. Then you can find the solution. But actually, if they just ask us one way to color, then you can stop here. But if you want to find all the solution, then you just continue, right? Backtrack, right? then you can find another solution. For example, this one. Okay. So that's the way for the backtracking. So why it better than the proof of search? Because you can see it can early stop, right? For example, when you color A green, B green, then it can stop here already. You don't need to color C and D anymore, right? Because it violates the condition. So you don't need to have the choice of C, have 2C, right? C green, C black here, right? Right? Because you already stopped here. Okay. You don't need to choose for C. So that's why backtracking better than the proof of search. You can cut a lot of choices. Okay. So understand? Right? Understand how the backtracking works, right? For every stage. So it means that if we index here 1, 2, 3, 4, right? So every time you just start with 1, right? You color 1. Then you call the recursive function to color 2. Then recursive function to color 3. Recursive function to color 4. Right? Then whenever the color 4 success, it means that you're already when you color D, you also check mark. Right? When you color D, you also check. For example, when you color D here, why it's not successful? Because D have the same color with A. Backtracking is better than the brute force search or the knife methods I just mentioned that you check on the combination, right? For the knife combination, when you color A, you color B, even though they are the same, but you also check A green, B green, C green, D green, right? But actually, when you color A green, B green, you can stop already. You don't need to check C and D, right? Right. So this means that you can stop. You can have the early stopping, right? Okay. So that's the idea for backtracking. So how we implement it? We create a recursive function that take the current index. So for example, A is the 1, B 2, right? We have the n index, right? 1 to V, for example, right? So we just take the corner recursive function with the current index. Then, if the current index is the number of the vertex, it means that we already reached the last one. Then we just bring the result. Okay. Okay. If not, it means that it can go, right? If, for example, it just go to the state I, right? Then because state I have the for the M choice, right? M color, man. So we just assign every color to M, to the state I, okay, or the region I. Then if we can check the configuration is safe, then we just recursive. It means that we can color the I is safe to color. It's just like that. It means when we color the B, right, with a blue, or we check, okay, whether B is safe or not, then we can see, okay, B is neighbor of A, and B and A have a different color. That is safe. Then okay, B already okay. Then we call the recursive function to C. Okay. So that's it. We call the next index. Call the function with the next index. Okay. Then you call the function with the next index, right? It means that you at the state I, right? You call the function of I plus 1. It means that you want to try to color I plus 1. But for example, I plus 1 return no, return X. It means that it cannot color I plus 1. Then you choose another color for I plus 1, right? For example, this one you choose for the green, but it return X, right? Then you choose another one for I plus 1, right? Like blue, right? Then if they return yes, then you just return yes to here, right? Right. So if return yes, then you break the loop and return the 2. You don't need to search anymore. If you just want to bring 1, configuration. You don't need to search for all the solution. You just need to bring down one solution. Then if the I plus 1 return yes, it means that they can color on the way here yes. Return yes here, then you break. You don't need to search for the yellow anymore, right? Because you already find the solution. This is yellow, okay? But you don't need to search anymore, right? Because here you can find one solution already. Then you can stop, you return. You said that, okay, the blue here is the correct one, then you return, okay? So that's the way we do. Then if on the recursive, on the color for I plus 1, return X, 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 mean that the color I, current color I will also X, right? Okay, then we choose another color for I. Okay, so that's the way for the backtracking work. So this is a real implementation. Okay, so this is the real implementation. So you can see, right? Okay, okay. So the recursive function, we call it, for example, rough colorful. This is a recursive function. Okay, so what is the parameter for this? How the parameter for this? Of course, we input the rough, right? Okay, input the number of the color. Okay, so this is the rough. Okay, this is the color, the number of the color. So for example, the color will be from 1 to m, right? Okay, number of the color, and this is the list of the color from 1 to m. Okay, so it store color 1, color 2, color 3, color m. Okay, and this is the color index. This means that we are coloring the index v. Okay, so we are coloring the index v. Okay, we try to color this one. Now, how to do? We just check the base case, right? I just mentioned. If v is the last one, last index, it means that we already reached the last one. It means that we can find the solution, right? We just return 2. Okay. But if v is not the last one, is not the last region, okay, then because we have the many way to color, so that's why we need a for loop. So it means that we try to color v with a different color, right? From 1 to m, because we have m color, right? So we check 1 first, 2, 3, 4, 5. Which one is the correct? Which one is the correct color for v? Okay. Remember, v is the index, and now we're trying to color v. Okay. And we have the different choice, right? We have the m choice, m colors. So we try on the color. We create a for loop to on the color. Okay. So we check whether the color C applied to V is fine or not. Okay. So yeah, to check how to check that, we call the ESET function. So ESET function very simple. It just check in the graph and find. Okay, this is the ESET function, right? It takes the what? It takes the index V, right? This is the index V, correct? And this is the color, right? The color we are trying to color to V. Okay, you remember, right? How to check is safe or not? Then you check on the adjacency matrix, right? You check whether on the neighbor, right? On the neighbor of V. Okay, this is the I, right? You look for the I. You check, okay, on the neighbor. For example, this is the V. Then you check on the neighbor. Neighbor, how you know this is the neighbor? This is the, for example, last one, right? So how you know this is neighbor? The neighbor means that the rough value, right? The index here equal 1. For example, this one equal 1, right? So if this one satisfies, mean that is 1, right? 1 and the color equal the color I. Okay. It means that they are neighbor. okay, this is the not I is the neighbor, right? It means, for example, in this one, 3 is a neighbor, for example, 10 is the neighbor because they have the value 1. For example, 5 I is the neighbor. And you check the color I. If the color I equal to the current color of the V, because C is the current color of V, right? Right? Because we try to color C to V, right? So C is the current color of V. Okay, C is the current color of V, and the color here is the result. You remember the final result or the current color we have. So if I is the neighbor of V, I is neighbor of V, so that's the graph VI equal 1, right? For example, 3 and 10 here is the neighbor of V. So I will be 3 or 10, right? And then color of 3 or color of 10 have the same color with V, because color of V is C. If they are the neighbor and they have the same color, then we return false, right? Because we mentioned that, okay, all neighbor must have the different color, right? So if they're neighbor and they have the same color, okay, then of course return false, right? Otherwise, if we check on the neighbor, then no neighbor return false. It means that no neighbor have the same color, then we return true. So that's the way you check how we know this is the sanctified or not, right? This is the except function, correct? Correct. So this is the we just define this function, then we can check whether we can it's set to color C or not, right? So if it's set to color C, then it means that we can color the not V with the color C, right? Okay. Then we just call the recursive function with the next index. It means that, okay, the index V, we can set to color. Then now we call the color V plus 1. Now we call the recursive function for V plus 1. It means that we try to color the next index. So it means that we call the recursive function. Okay. So if the V plus 1 return 2, it means that we can color V plus 1. Then we also return 2 for C, right? It means that when you color C, you can color on the subsequent nodes, right? So that's why you return 2. Okay. But if this one is not successful, it means that you cannot color V plus 1 with the color C of V. Then it means that you cannot color V with color C. Okay. Then it's not successful. Then you remove the color. Okay. For V. Okay. It means that V cannot color with the color C. Then you try another C. Okay. Right. You try another color for V. For example, C here equal 3. Cannot. Then you try C equal 4. Right. So it means that firstly we try one color for V. For example, C equal 3. The color, the third color. If third color cannot, then we try the fourth color. So how we know this cannot? We just call the recursive function to the next node. If the recursive function to the next node return 2, it means that you can color on the subsequent nodes. It means that you can color this node. Then you keep the result. You return 2. But if you cannot color the child node, right? It means that the number C equal 3 here cannot. You cannot color not V with the color 3. Then you try the color 4. 4 also cannot. Try the color 5. Until everything cannot, then you return false. It means that you cannot color any color for not V. Then you return false. Okay. So understand this problem? Except function, right? Except function. Okay. So this is the operator resident, right? This is n, right? Okay. So how the if condition happen? If both are true, right? Or both return 1, right? So both return 1, right? Or not 0, right? Both return 1 means that the graph V and I equal 1, right? So the left hand side, graph v and I equal 1. Okay, I erase here. Okay, so you have the two operate you have the and operator, right, with two arguments, right, left hand side and right hand side. Okay, so what does it mean here? If the if condition happen, it means that both of them will be 1, right, or both of them will satisfy. It means that graph vi equal 1, graph vi equal 1, I here. This means that I is the neighbor of V, right? Because we already built the adjacency matrix, right? If they are neighbor, then value will be 1. Okay. So if there is 1, this means that I is a neighbor of V, correct? Right? Okay. Then if I, then how about the second argument here? It means also it happens, it means that C equal color I, right? C equal color I means that I and C have the same, I and V have the same color, right? Because C, now you are coloring V, right? So I and C have the same, I and V have the same color, but I and V are neighbor here because graph VI equal 1. And color of I equal color of V. So it violates the condition, right? Because the color is the one that you are storing the current color for on the node, right? Right. So this is on the node V node. So you store the value for the color. For example, color of I is 3, color of V is 3, right? So the color is the 1D array to store the color of on the node. Okay. So color I equals C. Mean that NC is the current color of V, right? Right here. Current color of V is C. We are trying to color V with C. This means that the color V and color I will be similar. And V and I are neighbor. Neighbor but have the similar color. This means that it violates the condition, right? So it means it's not safe to color. So understand? Then you just run this recursive function with the index 1. It means that we start with 1. Then you can find the solution. Okay. So any more questions? Okay. I think today we stop here. On Friday, we will solve another problem with backtracking there called the A queens problem. Okay. So yeah, if you have any question, you can ask me, or otherwise you can leave. Okay. Okay. So yeah. So if not have any problem, then see you this Friday.